Well, hello, Internet, and welcome to my video on convolutional neural networks with TensorFlow. Thank you to everybody that's joining me. This is a live stream, so that means if you have any questions as I am covering some rather complex topics, guess what? You can just ask me live, and that is the whole reason I'm doing these live streams. Okay, so basically, what is a convolutional neural network? It sounds really complicated, but it's really not. It's just an automated learning process that is commonly used to and applied to analyzing images. So quite simply, what we're going to do is we're going to create models that are going to allow us to identify objects in images. All right? So pretty simple stuff. And I'm going to be doing everything using Google Colab. So for those people that don't have a really powerful computer, guess what? You can borrow Google's computers, and they are wicked fast. So what am I going to cover in this video? A lot. I am going to cover, well, good morning, Niz. Thanks for stopping by, and Deepak. I'm going to be covering how to upload data to Google Colab. I'll also discuss how to work with data if you have all this set up on your computer. I'm also going to cover gathering and preparing images, extremely important. Normalizing, which we've covered previously. And if you didn't watch the previous videos, don't worry about it. I'm trying to make each one of these self-encapsulated so that you do not need to watch all the videos to be able to understand completely what is going on. Normalizing, convolution, obviously, activation, and pooling. And I'm going to cover what all these things mean. Optimizing for performance. We are going to minimize overfitting. We are going to use augmented images, which are just going to be like doctored versions of the images. And it's an easy way to create more data whenever you don't have it. And also saving and loading models and a whole bunch of other different things. So, yes, eventually I'm going to get into machine learning for trading on the stock market. It's a progression. I'm just moving upwards, and you have to teach certain things before you teach other things. And there we are. Okay, so, and I don't know if your comments are showing up. No. Okay, so sometimes if you're on Twitch, your comments will show up. That's just the way that my system's set up. And if you're on YouTube, I see all of your comments. So don't worry about me being able to see it. I will see everything. Okay, so in the past, you may ask, if you saw the previous videos, we use different classification models to make predictions on things. And for example, one of the examples I like to say or talk about is, let's say you were trying to calculate the value for a home. Well, you would use things called features, which would be things like the size of the house, the number of bedrooms, the number of bathrooms, and so forth. And your ultimate goal would be to calculate the value for the home that it would sell for. Okay, so that's a lot of what we're going to be doing here. And in the previous videos, the models we created before, whenever we were classifying or using classification, what we were doing is we were creating things called dense layers. And the performance of our previous type of model benefited by creating many different parameters that were then connected so that we could see relationships. So for example, the number of bedrooms, the number of bathrooms equals the value of a home, okay? Features, number of bedrooms and bathrooms and things like that, square footage. The label or our goal is to predict the price of the home. I'm going to talk about a ton of different things as the video covers. Basically, I covered everything in the beginning of the video, what I'm covering specific in this video. Okay, so you may say to yourself, well, what is the exact process of creating? I'm just going to refer to them as CNN models from now on, just so that I don't have to keep saying convolutional neural network over and over again. What we're going to do, and you can see everything right here, is we are going to collect many images of like size, but they're not going to be a precise size. What I'm going to show you as the video continues is how to take any image of any size and then break them down so that they all have the same height and width. Yes, I am using TensorFlow for this video. Then what we're going to do after we collect all these images is we're going to split the images into training and test sets. We're going to think about potential labels and features, but in this situation, most of that is going to be done for us. We are then going to flatten our images into one big giant tensor, which is just, you can just think of it as an array. If you don't know what a tensor is, it's just a whole bunch of numbers that are going to be utilized to represent the image to the computer, because the computer can't actually understand the image in its current format. So what we need to do is change it into a whole bunch of numbers. We are then going to increase the number of hidden units. And what they do is they add weightings that are going to influence our desired output. See, what we're doing now is a little bit different than what we did previously. We were making predictions, like in the last video, I made predictions on wine based off of the chemical content of the wine. Okay, so they were very specific things. In this situation where we're working with images, we're not going to be working with very specific things. What we're going to be doing is actually teaching our computer to go in and look at an image and find features of that image. So for example, it might first off find just a line, and then it might find a curved line. And it's going to sort of use those different things and weight their importance to then hopefully predict. What I'm going to be doing is predicting whether images are images of pizza or images of hot dogs. Okay, so I did this from the HBO show. I thought it would be kind of a fun sort of thing to do. Okay, then we're going to use activation functions, and what they're going to do is help us decide what data is most important. You don't need to remember all this, and all of this code is going to go on GitHub sometime later today and it'll be deeply commented, so you can use this as a massive cheat sheet for your own explorations in this world. We're going to use optimization functions, and what they're used for is they're going to smooth the data to give us our expected results. We're going to mess around with learning rate, and the learning rate, one of the easiest ways to understand it is we're trying to get to a specific number that is going to be representative of either pizza or hot dog. And what the learning rate is going to do is how quickly we change our values to try to get to that number. Now, the positive of having a learning rate that is very big is you move to that goal very quickly. The negative of having a large learning rate is you might overshoot it. Okay, and I'm doing hand jive here with my fingers. And the other thing we're going to do is we're going to fit longer, which just means we're going to increase the number of tries that we have for fitting our data. And you can see here an example of all of the different weighting, or all of the different what we call hyper parameters. And I'm going to cover all of these in detail and exactly what they mean. And these are going to be the specific functions that we are going to use in our code. So the very first thing you're probably going to want to do if you're doing this on Google Colab is you want to get a hold of a GPU. And Google will more than happily give you one. And what we want to do here is we're going to go up till runtime. I'm hesitant to do this early because sometimes it will start putting up messages that you're not using the GPU. Hello, Farouk. Okay, so what you want to do is just go change runtime type, and you can see GPU is what I have selected right here. And then you're just going to say save. Okay? And what's really cool is you can come in and you can find out exactly what GPU you're actually borrowing from Google right now. And so all you need to do is just go ! And NVIDIA, if I can remember how to spell NVIDIA, -SMI, like that. And you can see that we are using a Tesla 4. So we're actually borrowing Google's high-end machines. You're going to see here all of the different things that we are importing. So we're going to, I'm basically just keep adding to this import list so that anybody that is following along with the videos can pretty easily, you know, just not really worry too much about all of the different things that we're importing. And as the videos continue, I explain what each of the individual parts are. I'm not going to explain every single individual part because I think it's more fun and more interesting to learn by actually running code and playing around with things. So what I'm going to use is a Kaggle data set. So we can just click on this, and this is going to show me what we have here are food images. And I have many, many, many thousands of them. And what you're going to need to do is you're going to need to download all of these images. And there's 6 gigabytes of them, but then you can just delete the folders that you don't need afterwards or whatever. So that is where all of our data is going to be coming from. Let's see here if I can find the folder where I have all this stuff. There it is. I have it on my Google Drive, but you can do all of this work if you just download it to your main computer. The only problem is if you download it to your regular computer, you're not going to have access to the power of Google's machines, which are wicked fast. I'm trying to go and actually show you all of this data. So what I have here is, let's just increase this. I don't know if I can increase the size of this easily. Let's do properties. What I'm doing is just looking at this file folder. You can see here are all the different images, and I can't zoom in, but hot dog pizza. And then what I'm going to do is I'm going to have a folder called hot dog and another one called pizza. And then inside of here are going to be a bazillion hot dog pictures. Yes, I know you can't see this, and I'm just going to get rid of it right now because I'll show you also that I have the exact same thing over here. Where do I have it? Whatever. Let's just get rid of that for now. And I'm going to have everything set up here so that you'll be able, on GitHub, if you download this code, everything is going to be all set up so you'll be able to very easily go through this table of contents and get all of this information. So it's going to be very, very beneficial to you. So, but I'm going to cover what happens if you want to actually just download this data, upload it to a Google Drive, and then utilize it from there. Now, the process is you're going to upload it to a Google Drive. I just created a folder that is called data. Hello. Nice to see you. There. Yeah, you can see the one comment that I have on Twitch here is showing up. That's just the way that everything's set up. All right, so what we're going to do is I'm going to zip the images folder for hot dog and pizza, those folders inside of there. I'm going to upload those to the Google Drive, and then what I did is I need to mount my Google Drive. I did this ahead of time. This is the only part of the code that is pre-done because I have to like give away private information that I don't really want to give away. So what we have here, let's see if I need to increase this a little bit so that you can see it a little bit better. I think that's better. Okay, so how we mount our Google Drive is you're just going to type in drive mount and content drive, and whenever you do this, it's going to pop up all kinds of information, your private information about your Google Drive account. So then the drive is mounted, and then to unzip the files, it's going to be content drive, my drive, and I put a hot dog pizza, the zip file, inside of a directory called data, and then you're going to extract all of it. And that is it, and now all of those files are going to show up in your system, okay? So, and you can see here's all the file directories and all that stuff. Okay, so after you go and you download all of those files, what we're going to have to do next, I'm having a little bit of trouble here with this one thing, is we are going to create a function that's going to allow us to analyze our data. Because whenever you're working on projects like this, sorry, I have to drink tea every once in a while, I'll lose my voice. When you're working on projects like this, you have to, the best thing to do is to start off by actually looking at the images and then being like, okay, yeah, this, I can easily see the difference between pizza and a hot dog in these images. Because if you get images that you look at and you're like, I can't really tell, which is totally possible if they're bad images or low quality or low resolution, you want to definitely verify that your data is recognizable. So I'm just going to create a function, and this function is just going to grab a random image from the directory and display it on the screen. So let's go to def like this, and I'm going to just call this display random image. And I'm going to say that you're passing a directory, and then you're also going to be passing a class type. And the directory is going to be the directory where all of your files reside here on Google Colab. And then the class type is either going to be pizza or hot dog in my specific situation. So what I want to do here first is define the directory to look in. So I'm going to call this image directory is equal to whatever directory that you pass inside of here. And then after that, I am going to do class type. Like I said, it's either going to be hot dog or it's going to be pizza. So there we go. After that, I'm going to get all the files from the directory. So I'm going to call this files and just go OS and list directory and image directory. And after that, I'm going to pick a random image from this specific directory. And how we're going to do this, what do I want to call this? We'll just call it image name is equal to random choice, like this. And it's just going to cycle through all of the files in that specific directory and spit one out. Then after we do that, I actually want to read my image. So it's going to call this image mp img. Yeah, img. And I am read and pass in the image directory plus and this and plus the image name. So image name. Okay, so now that we have that, I have my image that I read randomly from a directory, and what I want to do now is to actually show it. So I can just go plot, and this is matplotlib, what I'm using for all this, and you can see there's like little references. So this is an alias to matplotlib. So if you're not used to this stuff, that's what it is. And then you just throw your image inside of there, and then maybe I say that I want to put a title on it so that I can see that it is either pizza or it is a hot dog. And I don't want the axes to be shown because that's just going to be distracting. So let's get rid of that. And what else would I'd also like to look at the image shape, how large it is, height and width, so that I can verify that I don't have dramatically different sized images. Also very important to do. So I'll just call this image shape like that. And let's just do it like this. I think this will be easier. Image shape, and there we go. All right, so that is our function, and it is going to allow us to randomly display some images so that we can get a better understanding of what type of data we're working with here. Well, thank you very much, Eric. Okay, so let's go and let's get a random hot dog image just to see something. So I'm just going to say display random image, and the directory where I have everything stored here on Google Colab is just called hot dog pizza. And I want to, let's go and, oh, I think I have to throw that in there like that. Hot dog pizza, and let's say that I want to see a pizza just to start off. So does this actually look like a pizza or not? And oh, I forgot to run my directory here, or all of my imports. So let's just run that. It's blazingly fast. Yeah, people have asked, is it usable to use Google Colab to do machine learning projects like this? Yeah, actually surprising. No such file, hot dog pizza. Okay, well, then I guess I have to go and upload it. So I'm going to go off the screen here for a second. I'm watching on Twitch and YouTube, both at the same time. All right. So what I'm doing here is I'm giving it permission to access my Google Drive, and my private information's popping up on the screen. And I'm just clicking allow, that yes, it's okay to access my Google Drive. And then I'm going to unzip those files. And then I'll be able to get a hold of all of them. And it's just downloading. All right, so it's mounted. And now I am unzipping all the data. I thought I did this previous. And now we can come back inside of here. And let's run this. And it works. All right, so good. So there we are. We got a random piece of, or a picture of pizza. So we can come in and we can run this again, and it's going to give us a different pizza picture. And as we look at this, we can say to ourselves, all right, well, that definitely looks like pizza. Do the hot dog images look like hot dogs? So let's go. I think I called it hot dog like this. Let's run it. And wow. Okay, does that look like... Well, I would say that if all the hot dog pictures look this bad, we might have some problems. And that's the point. This data is not necessarily perfect because we don't want it to be perfect. We want it to be real world. And do all of these look definitely like hot dogs? It's a little iffy, but in general, we're going to just go with the data that we have. And as we go through, we're going to optimize it and we're going to make it work, basically. Okay, so how exactly do these, understanding how these CNNs work? Well, one of the great things is there is a website called CNN Explainer, and it is so super for really understanding exactly what is going on in these networks. And it is ultra detailed. Let's see if I can zoom in here if that benefits at all. And if I do that, then you can't see the end. Okay, so as you can see here, we have a whole bunch of different coffee cups, and you're breaking down all these different features using analysis of different color channels, so red, green, and blue. And then based off of that, I'll cover what all these mean. There's convolution, there's ReLU, there's all this stuff. There's pooling, you're seeing all this. And basically what we're going to do is we're just going to take all of this awesome information and we are going to be able to then go and make predictions in exactly the same way. So they say at the end here that this is indeed espresso. Maybe I should click on one of the other ones. So here is this a, oh, it's a ladybug. All right, so you can see this. All right, so the whole idea is to take the red channel, the green channel, the blue channel, and then find features within them that are ultimately going to give us ladybug as a final output. And basically how they do this is CNNs are going to apply filters to input images to learn how, like I said before, features like lines to start off, and then as it goes deeper, it might do curved lines, and then eventually it's going to look for very specific objects, okay? And they identify objects in an image by looking for these common shapes. And once they identify these common shapes, they then start making probability predictions on whether something would be a lifeboat, a ladybug, a pizza, a bell pepper, or a hot dog. Okay? And that is how they're all structured. Maybe I want to get rid of the chat box because I don't think it's really helping much. Okay. And these are called feature maps. And what they do is they record precise precisions of the features. Now, the potential negative is that slight changes can sometimes require a completely different feature map. And this is going to be addressed later on in the video with what is called downsampling. And with downsampling, a lower resolution version of an input is going to be created that still has the major structural elements, the lines and the curved lines, and ultimately the weird shapes that show up, and the difference between a ladybug and a pizza. Okay, that's just we're basically teaching the computer in exactly the same way that our brain is going to work. And what we have here, you can see this is going to be the input layer, and it's going to have 3 channels on it that are going to be represented with the RGB channels. We're then going to have multiple convolutional layers, and what they're going to do is they are going to weight different different features and then decide how those features differentiate themselves depending upon what the ultimate goal is for the image that we are searching for. We're then going to have an activation layer, which is, as we've talked about in previous videos, we're using ReLU in this situation. And what it's going to do is it's going to produce nonlinear decision boundaries. Later on, we're going to have a pooling section. What it's going to do is it's going to be used to produce, basically summarize the different features that are discovered and decide which are the most important. And then it actually doesn't have it on this website, but you're going to have also a flatten layer. And what it's going to do is it's going to convert a three-dimensional layer into a one-dimensional layer. And actually, then there's another thing that we're going to use, which is called softmax, which is another activation. And softmax is going to be used to scale from multiple different tensors into all of the different output probabilities. So what is the probability that this image is a lifeboat? What is the probability that this is a ladybug? The probability it's a pizza. Okay, so that's what all of those different guys are going to do. And as you go through this website, which is super awesome, you're going to see exactly how it's going and processing these images. And it's going to be moving from left to right. I don't know if you can see that. Let's zoom in here a little bit. So grab this and zoom in a little bit so that you can see. This is exactly what is going to be going on whenever it is going through the process of analyzing the images, and then it's going to translate them into a bunch of numbers. And it's ridiculously cool that stuff like this actually exists. Okay, so what you need to do is just kind of understand the hyperparameters. We're going to have a filter that is going to move across. Let's come down. I think this maybe is a little bit easier in understanding what's going on. So we have an input size. That's going to be the input size for whatever you're analyzing. So this is 5 by 5. We're not going to be working with 5 by 5 images, but this is just an example. You're then going to have a filter, and what it's going to do, if we can make this guy move around here, but basically it moves like this across your image, okay? And from left to right. And it's going to move across the image starting in the upper left, and it's going to proceed from left to right and then top to bottom, of course, 1 pixel at a time. You're going to see stride here, and stride just refers to the amount of movement between the different applications of the filter. And we can go and change this. Let's go and zoom out, and then you can actually see how changing the stride might actually work here. Oh, I have it. Let's pause, and then let's play. Is it going to work? I don't know. It's not working. Anyway, it moves across here. And basically, stride just means how much is it going to move. And for the most part, it's going to move 1 at a time. Let's get rid of that. I don't know. It's not moving. But anyway, is it going to move 1 at a time, or is it going to basically cover this area and then jump 2 spaces? Okay? And pooling. Do we have pooling in this situation? Basically, pooling, like I said before, is just going to summarize the different features and the detected input that we have here. All right, and I think let's just move into code because I've been talking way too much. All right, so there they are, and there is all of our stuff. Okay, so what we want to do here first is we need to prepare our data, which means we need to put it into training folders and test folders. And somebody just asked me a question. Can I make a video on how I remember what I'm learning? I use repetition systems, and then I just drill things. Like, for example, right now I'm learning how to play guitar. Just started 2 days ago, and how do you get good at it? You just do it all the time. The more you do it, the better you get. And and repetition systems can help with some of that also. There you are. And I have a couple videos on my website about that. Okay, so the data directory that we have here is called Hot Dog Pizza. And what we need to do here is we need to import this data, and then we need to turn it into batches of 32. I'm going to use images that are 256, so maybe I should put that in here. So I'm going to say I'm going to use images that are 256 by 256, and I'm going to have batches of 32 images. 32 images. Maybe I should write images. Okay, and the reason we're going to use 32 images is just to minimize our requirements. We can't load 1,000 images, or very often you work with way more than 1,000 images. You can't load all those into memory. So how exactly are we going to do that? Just moving some stuff around here. I have so many things open at once. All right, good. So what are we going to do here? Well, I'm going to create training data, and we're going to say tf caras and utils dot image dataset. I have to turn off my code completion, otherwise stuff goes all over the place. So image dataset from directory. So I'm handicapped here. Most of the time, all of this code just pops up here, and I just hit return. So a little bit slower. We're going to have to pass in our data directory that we're going to be working with here. And I'm going to say that I want 80% of all of my images to be used for training, and the other 20% are going to be used for testing. So how I do that is I say validation split is equal to 0.2, and then I'm going to call this subset is going to be training, and batch size, which means the number of images I'm working with each time through here, is going to be 32. Get rid of that. Batch size is equal to 32. And I also have to decide what image, because all of my images ultimately have to be exactly the same size. And a common, this isn't an ironclad, definitely every single time images are 256 by 256, but it is indeed a common sized image that is used. And then just to make sure that I get the same results every single time I run this code, I'm going to use a seed of 66, because the weightings, whenever you are making predictions about your images, actually, crazy enough, start off being random. Yes, the very first weighting for the image is a completely random value. Looking at your comments here. Well, thank you very much. All right, so let's just come in here, and I'm going to do the same for my validation data. Validation data. And again, we're going to do basically the same exact thing in this situation. Data directory, and I'm going to call this, let's call it validation. And 32, 256, and 66. So we got all of that stuff all set. Let's run it. As long as I typed it in right, everything should work. And it's going to give me information on, oh, I spelled validation wrong. I cannot let that go. All right, validation. All right, so we're going to have 2,000 total files. I have 1,000 pictures of pizza and 1,000 pictures of hot dogs. Two classes. The classes are hot dogs or pizza. That's why we have two classes. I'm going to have 1,600 files for training and 400 files for validation. So, and validation just means that I'm going to test to see if, you know, I'm able to make predictions on images that my model has never seen before. We can come in and we can get our class names. So let's just go class names and training data and class names. And then we can come in and let's just print that out. Class names, like that. And you can see hot dog and pizza show up. Now what we need to do is remember everything's color channels. So it's looking at a pixel and it's saying how much red, how much green, how much blue is in these different images. We can't work with that because those values are going to go from 0 to 255. What we want is all the values to be between 0 and 1. That is called normalizing, whenever you go and get those values and shrink them down. And how we normalize all of this data, I'm just going to call this norm layer is equal to TF and caras, layers, and rescaling. And you just, if your maximum number is 255, well, you just go and divide all of the values by 255. Boom, problem solved. Okay, and now what I'm going to do is training data norm is I'm going to go and get my training data. Really missing my autocomplete. training data map, and then we're just going to apply this normalized layer to all of the different images. So we're going to cycle through all of these different images, and then we are going to output and resave all of them so that, remember, the maximum number is 255, so we're going to divide every single thing by 255, and that's going to guarantee that all of our values are between 0 and 1. Very important. And you say, well, why would you do this? Well, machine learning models work best with normalized data, so you always want to work with normalized data. And you can't have things on different scales. Like in the last video, I talked about how, like we had values. We were looking at the chemical content of different types of wine and making predictions off of whether judges would consider it to be a good wine or not, and how we had sometimes 400 as a value, and other times we had like 0.001. So all of that needs to be normalized so that everything is of the same exact scale. And this dumb watch is talking to me. Okay, so I think that's understandable. And why? And we're going to do the same again. So let's just copy this. And let's call this validation data norm. Validation data norm. And then this is going to be validation data. Validation data. All right. And everything else there looks like it's good. Oh, norm. This is layer. Whoops, that was probably causing confusion. Sorry about that. And we can run that. All right, and now what we can do is check to make sure that all of our data has been normalized. So I'm going to say image batch and labels batch is equal to, and next, and I'm just going to iterate through the training data here to make sure that it has all been normalized. And when I take my break to get some more tea, I think I might also turn on code completion because it's driving me insane. So let's go and get to the last, or the very first one. Okay? And you can see now everything is between 0 and 1, precisely the way that we wanted it to be set up that way. Okay? All right. So now what we want to do is I'm going to show you the last time I'd used a non-convolutional binary classification method for determining whether wine was either considered good or bad. Well, now what I'm going to do is I'm going to do exactly the same thing, but I'm going to use hot dog or pizza as the potential options. So, and we're going to be able to compare what we did in the previous video, which worked excellent for analyzing what we were analyzing, and compare how it works in this circumstance with analyzing image data. Now, if you can remember, we went random seed. Again, we are going to be setting this, or this is going to be random.setSeed. We're going to be setting this to a value so that we can reproduce this randomness in the future. I'm going to call this model 1, and what we're going to do is as we proceed, we're going to just create more and more models and see how our different changes are improving our overall results, which I promise you will get dramatically better. Okay, well, the first thing we need to do is we need to flatten all of this data because I don't really want, it's fine, because everything is going to be spread out in 3 dimensions. We need to sort of crush it down so that it is one vector that we'll be able to work with. So I'm going to say flatten, and I'm going to have, and I went and converted everything to 256 by 256, all of the images. So I'm going to set the input shape to be equal to 256 by 256 and by 3. The 3 part is the 3 different color channels that we are working with here. I'm just verifying here. This is supposed to be here, like that. There we are. Okay, so let's get rid of that so that doesn't cause any other problems. Okay, then we're going to add layers. And I covered this previously, and I talked in this video about ReLU and how it's going to smooth everything. And I'm going to grab this dense layer right here, and we're going to make multiple different layers. And let's get this and put, whoops, that there and that there. There we are. And I'm going to use 3 different layers here. And what these are going to do is they're going to be going through and trying to make sense of the image data that it has and try to find connections between that image data and ultimately what we are going to be working with here. And then finally, we're going to have sigmoid. Okay, and that is all of that. So that's the beginning of our model creation. And try to keep this all on one screen. Well, after we create the model, and I covered this in massive detail in the last video, we need to compile the model. So we're going to go loss is going to be equal to, we are going to be working with either, our results are either going to be a pizza or a hot dog. So in this situation, it's going to be binary. So this is going to be binary cross entropy. And then we are going to define an optimizer. And I'm going to use Atom exactly like I used in the last video because it worked out pretty good for us. So optimizers and Atom. And then I also want to get some metric data on the accuracy, like how accurate is my model. So I'm going to say the metrics, or the metrics that I'm most interested in is accuracy. So here is all of that. And after we go and compile that, then we fit. And that just means we run through and test and look for features multiple different times to see what type of different results we can get. All right, and I'm going to call this history 1 because this is my very first model, and that is what I want to work with. So I'm going to say model 1.fit training data, and I want to work with my normalized data. And I am going to run this 5 times. Let's try that. And then validation data is going to be, again, the validation data that was normalized. So norm and validation steps is going to be equal to the length of the number validation data norms that we have. All right, so now that we have all of that set up, we can go in and build our first model analyzing these results and see if our old way of analyzing data is going to work in this circumstance. And you can see here our accuracy is 50% on our first run through, and again it's 50% and not looking that great. Don't worry, this is on purpose. I'm just showing you how convolution networks are going to provide dramatically better results than what we had before. Well, you can see our results are 0.4650. Okay, so not very good. Don't plan on doing anything deep learning wise with C++ because what I do for a living is deep learning stuff using Python. So there's really, you know, it wouldn't make any sense for me to try to do something that that I personally don't use all the time. So sorry, but yeah, that's probably not going to happen anytime soon. All right, so if we want to go and get a summary of what we did here, you can see we got terrible results, and we had 786,436 parameters, and we still got absolutely horrible results. So yeah, not good. So let's move on. Maybe we want to come in and maybe we were ironclad. We're like, nah, we're going to continue with the old way of doing things, and all we need to do is just add more layers. All right, I'm going to save ourselves some time. I'm going to actually just copy all of this, come up here, and I'm going to paste it down here, but I'm going to add a ton more layers because this is the way that we would have solved this type of problem in our last video. Is we would go in and we would just add more layers, and then magically all of a sudden everything would get better. Well, let's add 100, and let's add another 100, and you can keep going if you would like. So let's go and copy this. Maybe we want to go and add another 100. And sigmoid, do I need to change anything else? I don't think I do. So I just added a ton more layers. I could add more epochs. I could do all of that stuff. Oh, and make sure this is changed to model 2 because we don't want to mess up anything else. And later on, maybe in the next video, I'll cover TensorBoard and how it can be used to analyze all of your different models all at one time so you can see how they perform. Now let's run now. Let's see how our accuracy is going to come out now with all of this way more complicated model. Well, you can see we're up to 62%. So that's a major jump up from 45%. And it's going, and oh, look at this, we're up to 71%. So, hey, maybe we don't need convolutional neural networks anyway. And whoops, accuracy just fell to 56%. Maybe we don't need these after all, and I can just cancel the rest of this video. All right, well, let's come in here. And we're not working with much data, which is, of course, another way to dramatically improve our results. Let's come in here and do a summary, and we'll see how many parameters we're working with now. Now we're jumped up to 19 million different parameters. So we went from, what was it, 786,000 to 19 million by adding. But you can see here, are our results dramatically better? Yes, they are. So what I said in the last video, that you can add more layers and you can add more epochs and so forth to get better results. Well, I proved myself right by showing that. But what we want to do is we want to take it to the next level, which is going to require us to create a convolutional neural network. And I'm going to do that right after I go get myself some more tea because my voice is dying. So I'll be back in a second. All right, I'm back. And just checking my microphone levels just to make sure you can hear me. Some questions. Yes, I'm going to be covering a lot of different types of convolutional neural net CNNs. I'm going to say CNNs. The useful CNN. I don't have love for the news media in my country. What do you say? Yes, I'm going to cover that. I'm going to be covering probably transfer learning in the next video, along with a whole bunch of other different things. I just spilled tea all over myself. Somebody asked about repetition systems and having trouble. I don't know. I just keep adding stuff to repetition systems like Anki, and I just study them over and over and over again. A lot of you guys know that I'm not, well, some of you people know that I'm not the world's greatest chess player, even though that's the one thing I've really struggled with, probably more than anything else I've ever done in my life. Like, I just picked up a guitar for the first time, 2 days ago, and I'm already playing a whole host of songs. So some people just have blocks for learning certain types of things, I guess. One of the things that I have a block for is learning chess. But the repetition system sort of failed me there unless somebody plays accurately. It's hilarious. I have beaten 1,600 rated, 1,700 rated players, and I lose to 500 rated players. So I know that's a common question people have. I don't know. Well, thank you very much, Hiker James. So I don't know. That's just a thing. I use repetition systems, and I think you get good at what you do a lot. And I think that the reason why I'm getting good at guitar so extremely fast is I say that I'm learning it for 2 hours a day, but it's probably more like 3 hours a day. If you do something for 3 hours a day, every single day, for a month, you will get good at it. I promise you that. It's almost impossible to not, unless it's me and chess. but languages, foreign languages, programming, all this stuff. If you have a proclivity for that type of stuff, then you'll get it. And a lot of what I excel at is logic-based things, and I guess eye-hand coordination. I'm good at those things. And guess what? If you look at my channel, almost every video I've made has something to do with logic or eye-hand coordination. And things that are not based off of logic or eye-hand coordination, I'm terrible at them. I just don't, I don't know what it is. So, yeah, you beat me in chess. All right. Well, good job, Eric. Join the mile-long list. So thanks for talking to me. I'm looking at all your comments. So just know that I am looking at them, even though they're not on the screen. All right, let's get back into coding, and let's actually make a convolutional neural network, which was the whole purpose of that. So let's see how many total number of batches of 32 images I have. So I'm going to say, I'm just verifying you can all see what I'm doing here. Let's put this up here and maybe shrink this down. Seems like most people here are from YouTube, which makes sense. The only positive is with Twitch is some people have said that the resolution's better. I have no idea. That's why I'm doing it in doing live streams in multiple different places to see which is better. Okay, so we have our training data, normalized training data, and guess what? It's probably going to be 1,600. Remember, we have 800 training data images and 200 validation data images. So let's divide this by 32, and if we do this, we should get the same value. We do, 50. Okay, so that means we are going to have 50 batches of 32 images that we're going to be working with here. Now, how much of this code can I copy? Maybe for the first time, I'm actually going to go and type everything out. So I'm going to say model 3 is equal to TF and Keras and models sequential. We're still going to be using sequential. It's going to look somewhat the same. And let's look at basically what we're going to do here. Let's get this out of here. What we're going to do is we are going to model what they have on this Polo Club site here. So we're going to have convolutional networks. We're going to have activations. We're going to have a flatten layer, which isn't on here. We're going to have pools. And I'm going to explain what all of those individual things are as we continue onwards. So let's go back. I'm going to tab back here so this isn't quite such a mess. Okay, so we want a convolutional network. Here we go. Well, thank you very much, Eric. I greatly appreciate it. I really value you everybody here. And if you regularly comment on my videos, I read all my comments and I answer every single comment that I ever get. So, okay, so what we're going to do here is we're going to have filters. Remember what filters are. Filters are the things that move across the screen on the image. Okay, so let's go back here and look. All right, so let's zoom down. My mouse is very slow today. What is it doing? So silly. Okay, there, it got it. These guys. I'm trying to look at. Okay, see, they're going to move from left to right across our image. Okay, so that is what I mean whenever I refer to those. And what I'm going to do here is I'm going to go kernel size. The kernel is going to actually be the size of that block. So it's going to be 3 by 3. You can either type it like this if you want to, but if you don't enjoy typing, you can just type 3. That works also. Activation is going to be RelU, just like we used in our previous videos. And our input shape is going to be 256 by 256. Remember, we went and we made every single image that we are going to be analyzing at 256 by 256. I think you can rewind, I don't know. I just started doing convolutional neural networks, so if you just tuned in, that's what I'm doing right now. Some of the stuff might be a little bit confusing, but I'm going to go back over and explain what all these individual pieces are. So if you just literally tuned in, all you really missed was the beginning of a review of me trying to use all of what I knew previously, what was in the last video, and apply it to analyzing images. And as we saw, we got pretty good results. We got 75 something accuracy. That's not bad. It's fantastic, actually. Okay, getting a little bit distracted. Let's make sure I got my parentheses right. Yes, that's the right parenthesis, and I don't think I want this down here. No, I do not. Okay, so then we are going to, another way of doing this, I sort of typed everything out just so I could talk about each thing individually. You can also just go 10, 3, and activation is equal to RelU. So if you don't really enjoy typing, well, there you go. You're going to have to define your input shape, though, whenever you're getting this, because it needs to know what size images you're going to be working with. And let's go and add in another one. And we're going to work our way up to the CNN explainer way of doing things. So we're going to start off small, and then we're going to work our way up until we get basically the same types of results. FD God, you are very welcome. Okay, so what do we need to do now? Well, we're going to need to flatten so that everything is all in one layer. And then we need to go and actually output one binary value. So what this last part is going to do is it's going to say that I want 1. It's either going to be a hot dog or a pizza. So for FD God, what we're doing here is we're inputting a whole bunch of pictures of pizzas and hot dogs, and then our model is going to say this is a pizza or this is a hot dog. And what this last part does is it says I want either pizza or hot dog spit out as an answer. So we're going to say sigmoid is going to do that for us. Okay, so I got all of that. Now I just need to compile all of it. And let's bring that up there. So I just say model 3 and compile. And loss is equal to, again, we're either going to have one or another result. So we're either going to have pizza or we are going to have hot dog. So binary, that's what that means. And optimizer is going to fit this data, these images and the shapes in the images, and try to make predictions. So Keras, optimizers, and atom is what we're going to use, exactly like we used previously. We're just flattening everything down from multiple dimensions down into one flat piece. That's all. That's all we're doing with it. And what else? Oh, metrics. We want to be able to see the accuracy of our model versus the the training data versus the validation or testing data. Okay, and that is going to allow that to go through. And then I am going to, let's call this history 3 is equal to model 3. And after I do all this, I'm going to go through and walk through and explain every single piece here as I go through. So if it's not totally making sense, it will in a minute. Data, I need my normalized data. And this is all going to basically be the same too. I'm going to define that I want to step through 50 batches of 32 images at a time. So steps per epoch is going to be equal to, and it's going to be the length of training data norm. So it's normalized data, meaning values between 0 and 1. That's what I turned all my pixel values that are different amounts of red, green, and blue all into data that's going to be like different percentages of red, green, and blue that are going to be between 0 and 1. That's the point of that. Don't worry about it. As I do this, I'm going to explain everything as I go through. Okay, so validation data is going to be, and this is going to be, we're going to use a certain amount of our data, 800 images to be precise, or 1,600 images, depending upon how you want to look at it. And the other 20%, we're going to then be like, okay, I created a model based off of analyzing these 800 images. Now I want to test the performance of that model versus the other 200 images that the model has never seen before. And we want to see how good that is. So validation data is just going to be validation data norm. And then we need to define, step through the data again, 32 images at a time. So validation steps is equal to length and validation data norm. Okay, and there we go. We just created a convolutional neural network, and let's run it. If I don't have any typos, it will do it. And then I'm going to break down exactly what each of these individual pieces are doing. It's taking its good old time here. There it goes. That's working. All right, so how good is it going to do? Let's see how good our performance is. Well, our accuracy to start off is 55. That's not that great. Don't worry, I wouldn't be showing you all this if this was terrible, if the performance was bad. I wouldn't be wasting my time. Oh, you know what? I forgot to put the number of epochs in there, so it only did 1. So let's go epochs. I was wondering why it was only doing that. Let's try 5. Okay, so 5 epochs. Well, now you know what happens if you don't put the number of epochs. It just does 1 and then it stops. Okay, so here is our accuracy, and it was 50 something. Oh, 62. It went up. And what it's showing here is the accuracy with the training data and then the accuracy with the validation or the test data that it's never seen before. How much did you miss? I just created the first convolutional neural network. What you missed was me showing how all this stuff is going to stay on YouTube, so you can watch it afterwards. And all of this code that's going to be ridiculously heavily commented is going to be uploaded to GitHub after this is all over with. So you didn't really miss anything. But what you missed was I showed how to upload images to Google Colab, and then I used the techniques that we used in our last video to analyze whether wine was good or not. And I tried that with image data, and we got half decent result. I think we got like 70 something accuracy. Well, our first test with our convolutional neural network came back with a 71% accuracy. So that is pretty fantastic. Now what I'm going to do is I'm going to sort of explain exactly what all of these individual pieces do. Okay, So what we have here, this is a convolution. And the technical thing that's going on, I'm not even going to tell you. Basically, a convolutional layer, it just contains filters, okay? And you can also, sometimes you'll hear filters referred to as kernels. You can see there is a kernel there. And they are used to recognize patterns that are present in images. And our final output is going to be a vector. Question, can that operation be visualized? Well, I use CNN Explainer. CNN Explainer is a fantastic website that shows how it takes an image, breaks it down into red, green, and blue color channels, and then it uses those to see patterns based off of different color channels, and then ultimately what it does is it makes predictions. So let's zoom out. So here we have a ladybug. That's what I selected up here. And you can see it goes through all these processes and uses all these different functions until it finds different patterns that are common for ladybugs or lifeboats or pizzas. And then it makes predictions based off those shapes. See, that's the point. There's consistent shapes that are found in certain types of images, and they're not found in other types of images. And we're just looking for those shapes. And then once we find those shapes, we go, hey, that's exactly what our brain does when we look at something. We're just teaching a computer to do it. We're saying if you see, like for example, if we would be looking at a pizza versus, I'm trying to think of something, like a hamburger or something like that. Well, it's very common when people get pizza, they get pepperoni on the pizza. So something that would be common is a whole bunch of circles is a sign that this is pizza. And a hamburger would be one big giant dark brown object in the center. Okay? So that's kind of like a way of utilizing that. Pizza, they tend to have sharp angles because you cut a pizza like triangular, while a hamburger has sort of a round shape. Okay? So we're just teaching the computer to see round shapes or see triangular sharp angles, and then being like, well, when I saw a sharp angle before, that was labeled a pizza, which is ultimately, it gets all this data, plus it gets the correct answer at the end. So that's what this thing's doing. It's looking for those weird shapes that make something a pizza versus make something a hamburger, or make something a hot dog versus make something a pizza. All right? Hopefully that answers your question. And this site is wonderful for really understanding convolutional neural networks. This is it's a wonderful site, and basically we're just recreating everything. Okay, so back to what I was talking about. All right, so basically it has a whole bunch of filters and kernels. Kernels are the things that move across the image and look for specific shapes, and then it looks for different patterns within it. And here specifically, we have a 2D convolutional, this function, convolutional layer. The filter is going to be how many filters should pass over input. And normally, you're going to see values like 10, 32, 64, 128, or more if you have very, very complex models. The kernel size is just going to be how big the filters are. Remember this guy right here? So it's going to be, I don't know why this site actually kind of broke. Let's see here. Where is it? Lost it. Okay, so here is our kernels. And I don't know why it's not showing. But this is a 2x2 kernel, so that means the kernel shape, these are pixels. So it would fill up here, 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 and here. And that's the kernel size, all right? So that's what in our circumstance, we're using a 3x3 because we're using a 256 by 256 pixel image to analyze. All right, so hopefully that makes more sense. As per padding, I already talked about that. Basically, what it's going to do is it's going to put padding around the outside of our image. And that is just to make sure that at some point in time, each pixel is going to be in the center of the kernel. Let's see if I can, there it looks. Okay, let's look. So if you have your kernel right here, this is going to be hit once, and then it is going to be it's going to be hit multiple different times. So by increasing padding around the image, that's just guaranteeing that every single pixel is going to be looked at. All right. So that's what we're going to do for that. Input shape, 256 by 256, and strides, and so forth. And I think I covered everything that we can talk about there. All right. And basically activation functions are just going to help our network decide which data is important and which data is not. And it's going to apply different weightings depending upon whether it sees data as being important or not. So if it sees a specific shape and it's like every time it sees that shape, it's like, hey, this is a pizza, then it gives high weight to that shape. And if it sees hot dog shapes, then it does the same there. Okay? So let's see how accurate this model was. What is this, model 3? Sometimes I talk so much I like lose what I'm talking about. So let's come in here and let's go and actually model this out and see how good our accuracy is versus our how good our accuracy is with our model that we just created. So this is history 3, and call history on it. And then I'm going to plot this out. I'm going to say that I want a figure size which is equal to 20 by 10. And let's see if it works. And let's look. Okay, so what is this telling us? Well, the loss is decreasing, so that is going to be really good. Accuracy, which is the orange thing right here, the accuracy is increasing. So the blue and the orange are going to be the loss, meaning how inaccurate was our predictions, and accuracy is just going to be how accurate was our predictions. So as we can see here, the loss is going down, so that's good. Our accuracy is going up, so that's good. And however, you can see that whenever we use our validation data or our test data, that it is rising, and that is not good. And our validation accuracy is actually going down. So those are all bad things. And what this is a sign of what we call overfitting. And overfitting is probably best understood. Let's say your process of studying for a test was getting a textbook and just looking at whatever the question was and then memorizing what the number was at the very end. Okay? Well, you might, if you were literally handed your textbook and that's what the test was, you'd get a perfect score. But whenever you're just memorizing the training data, you're not understanding the concept that is actually going on in solving the problems. And that's what overfitting does. It gets highly accurate whenever it's looking at the training data. It's essentially memorizing the question and then saying, anytime I see this question, I should answer with this number, versus actually understanding the concept itself, which would allow us to look at similar types of problems and also be able to solve those. So how exactly can we get rid of this overfitting problem? Well, one thing that we can do is pooling. So, and I talked about pooling before, and what I'm going to do is now show you exactly how to use it. So we're just gonna throw in another layer. That's all we're gonna do. So let's go and grab that. And let's come down here, past this, and let's just paste this inside of here. And to start off, let's call this model 4 and model 4 and model 4 and model 4. And all this stays the same. So we have filters, kernel size, ReLU, input shape. All these things are exactly the same. Well, thank you, Dan. I appreciate it. But the only thing that's going to be different here is we're going to throw in. And if you look at the CNN Explainer website, you can see that they use a pooling layer inside of it. And what it does is it just tries to find the most important, breaking down the most important of the most important shapes that we have here. But you don't have to worry about doing all the crazy math or any of that stuff. You just type in max pool 2D like that. And then we're going to say pool size. And I'm going to set this for 2. Again, you can type in 2, if you really like typing. If you don't really like typing, then just type in, whoops, just type in 2 like that. That'll work. And then I'm going to also use padding, and I'll mark this as valid. And you can also put the put same inside of there. What we're going to use valid in this circumstance. And I said before that we add padding to keep our image from shrinking down, because it would actually shrink down otherwise. Okay, so let's go and let's use polling multiple different times. It's a great way to eliminate overfitting. It's not the only way. We're also going to talk about augmentation. Okay, so let's do that. And are we going to do any more after that? Well, let's just throw, we actually don't need to type all this in. Let's just go max poll, because these are actually default values. So I'm just going to, the values that I typed in, I just wanted to talk about what they were. But I talked about padding and pool size and all that stuff before, so I don't need to talk about it again. Okay, so we got that, and this is still going to be sigmoid and binary cross entropy. I don't need to add anything else here, and no, I do not. So let's see if this is going to solve our overfitting problem that I think I've explained quite well. Thank you very much, Keith, the developer. Well, thank you very much. I'm very happy to hear that when somebody says they refer me. Oh, look at our validation. It's getting pretty good. 80%. Getting a lot better. We're just doing 5 epochs. 81%, and we're going to just keep making that up, drop down to 78. Okay. So let's go and actually see how good we really did, because we want to plot this out. We don't want to just trust what we're doing here. And I'm just going to copy and paste this because I don't feel like typing that again. Okay, so let's go history and paste this inside of here. And then let's just change this to 4. Boom. Okay, are we doing good? All right, so here we have our loss going down, great. We also have our accuracy going way up, also great. Our validated loss, this is, remember, how off our predictions were on test data that our model never saw, so that's green. That is going down, and then it's going up. That is not good. Validation accuracy, once again going up and then going down. That is also not good. What does that mean? That means we still have an overfitting problem. That's what this looks like. This is an overfitting problem. Whenever your loss or your accurate, let's just talk about accuracy. When your accuracy is better, way better, in this circumstance it is, way better than your test data accuracy, that means you have an overfitting problem. So how can we get rid of it? Well, another thing we can do is we can add more data. But you might say to yourself, well, I don't have any more data. I have 1,000 images and that's all I have, and I guess I'm just done, and the best I can do is 78% accuracy. Nope, because we can use something called augmentation. What augmentation does for us is it's going to take our images that we have and it's going to shift them, it's going to turn them, it's going to zoom them, it's going to shear them, it's going to crop them, it's going to rotate them, it's going to flip them. And in doing so, it's going to create an infinite variety of more different images for us to analyze. So, what are we going to do here? Well, I'm going to go data augmentation like this and sequential, and you're going to be able to add, like I just said, you're going to be able to crop, rotate, zoom, flip, and so forth. I'm going to add some of those changes to our images that we have right here. So I just need to define exactly how I want the images to be changed. So you say layers, and I leave this to you to go search on the internet for different things. Let's say that I want to randomly flip, and I'm going to say horizontal and vertical. So I'm going to randomly flip horizontal and vertically these images, and also I am going to rotate them. So I'm going to say layers and random rotation. And let's just go 0.2. I think that's 0.2. It might be a 20%. I'm just going to stick with this, and if I get really terrible results, I'll know it's a 20 instead of a 0.2. Sorry, I don't have every single thing memorized. Okay, so that's what I want to do. I'm going to take these images, I want to horizontally flip them and vertically flip them and randomly rotate them around. Okay, after I do that, what am I going to be able to do? I'm going to be able to utilize those to go and make more predictions. So let's come up in here. I'm just going to copy this again because why go and type it out again? There's no point. So let's just copy that. I think I actually hit Control V. I hope I did. Yes, I did. Okay, so we're going to, this is our 5th model. You've made, if you've followed along with this and you work through this, you're going to create 5 models minimum. That's what we're going to start off with. All this is going to stay exactly the same. Polling size is going to stay exactly the same. I do not need to change absolutely any of this. So all of that stays the same. And what we want to do here, let's say, Now let's see. I'm sort of perplexed by a problem I'm having. I'm having minor technical difficulty. I'll be back in 1 second. All right, I'm back. Okay, so what we need to do here is just go and apply the augmentation to our data here, and then everything else stays the same. So we'll go data, augmentation, like that. And I don't believe there's anything else I need to change. That's it. Oh, yes, I do. I need to change all these to 5, otherwise I'll get all kinds of things and I'll pollute all of the wonderful work we've done before. And everything else is exactly the same, though. Okay, so let's run that. And we will see how good our results are at this point. Maybe we want to take it up at even more epochs, because I think this is probably going to be the last time. Well, I'll leave it. Maybe I'll take it at least to 10. And then we can go and test to see how our accuracy is working out. So there we are, 75%, 72%. Hopefully, oh, you can't even see this, can you? There, you can see it now, right? This is the problem with doing live streams. Okay, so we got it up to 76% accuracy, and let's take it up to 10 epochs. And then after we do this, we will go in and actually test to see if our how accurate our final results are, and if we solved our overfitting problem. And covered a lot. Oh yeah, I did increase the epochs. I just did. I just looked down. I just increased the number of epochs, and then I looked down, and somebody said, "Why not increase the epochs?" Well, I did. All right. And then after this, we're going to test to see if our accuracy has improved. We got rid of that overfitting problem, and then we'll discuss how to further improve. This would be like homework for you, some things that you can test out on your own, because that's good. That's the only way to get good at this stuff, is to just, you want to know how to get really good at building models? Make lots of models. Look at that, 82% accuracy. Don't worry, we're going to test this on images that we have never seen before also. So 82% accuracy, that's pretty fantastic. And in the next video, I'm going to show you how to make that number go up to like 95%, 96%. Okay, so let's throw this in here, and this is 5, and run it. Did we get rid of our overfitting problem? Yes, we did. So here is our value, our validation accuracy. It is above our regular training data accuracy, and you can also see down here our loss. So the green, the loss is lower for the validated data versus the training data. Overfitting problem solved. It's wonderful. So how can we further improve our accuracy? This is going to be some homework for you, but I'm also going to do a prediction on a custom image that was never seen anywhere. I'm just going to upload an image and test it. And then I'm also going to show you how to save this model so that you can use it over and over and over again in numerous different applications, and also how to reload it. So what else can we do? Well, we can increase the number of layers. We can add more convolutional layers. This is stuff you can try for your homework to see if you can get above, 82% accuracy. You can increase the number of filters in each convolutional layer. I'm only using 10. Like I said, it's very common to use 32, 64, 128. You can train for longer, like our friend here said. You can add more epochs. You can find the ideal learning rate. I showed how to do that in the last 2 videos. So if you want to learn how to do that, go check that out. We use a callback with a scheduler to go and constantly change the learning rate, and then we can see where the learning rate is the best. And of course, we can get more data to work with. All right. So what we want to do now, we created this model and it says it works and it says everything is wonderful, but is it really? I do not know. So let's go and try to make some predictions on that. Where is this actually stored? Trying to figure out how to upload my pizza here. Here, give me 1 second. I'll be right back. There, so I'll be right back, and I'm right back. Okay, so what we're going to do is, again, I'm just going to put this in the Google Drive and, get it in Google Colab. You can use any online storage. You don't have to use that. And if you're just on your own computer and you have this in the same directory as this file, you can do the same thing. You just do something like, let's just grab this, and it would be like this. And then you would have, like, if you had this image, for example, in the same directory, you could go mpeg like this or mpeg like that, depending upon what you have. So this is Google Drive. This is if you have the image on your own computer. All right. So I got our image, and let's go and actually look at what the image looks like. So image show, and whoops, just to verify this is a piece of pizza, because if it's not a piece of pizza, that would be very embarrassing. And let's get rid of the axes, because I don't like that. It just makes it look bad. Okay. Boom. Yeah, it looks like a pizza to me. I just downloaded a random piece of pizza. Our model has never seen this in our training data or our validation data. It's no idea what this is. Now, let's go and look at the shape of it. So I'm going to say my pizza and shape. It's 256 by 3. And one thing is going to be, if we tried, like normally what we would do is we'd say model, this is model 5, right? Model 5, yes, model 5. So previously what we did was we would just say model 5 and predict and throw in my pizza. Like that, it's not going to work. Can't do that, and the reason why is the dimensions are different on this. So this is not going to work. So let's just get rid of that. Let's get rid of that angry message that we have there. All right, so there's nice pizza. I'd much rather look at that. So how are we going to correct that? Well, one thing we want to do is we want to go and actually verify that our data is normalized. So let's go and see what my pizza actually looks like. So let's run it. No, does this look normalized? It's not normalized, so that's not good. So let's get rid of that. And what we're going to need to do here is we're going to normalize and resize our data. So this is 256 by 3. That's wonderful. We don't need to resize it. But sometimes you might get images that are not 256 by 3. And so I'm just going to show you how to normalize all of it. So I'm going to go and get my pizza, and I'm going to read in this image that I have here. Well, actually, let's just use that. Yeah, I don't need to do that. So you would just read that, but in this circumstance, I don't need to do that. So let's do this instead. So what I want to do is I want to turn this file into a tensor. So to do that, you just go tf.image.decode image my pizza, and then I need to resize it. So I'm going to say my pizza. I'm just overwriting it over and over again because it doesn't really matter what I do. So if I want to resize it, I just go tf and image.resize, and I'm going to pass in my pizza, and I'm going to say that my new size, even though it's 250, I'm just doing this for situations in which you don't have 256 by 256 images, so that's how you resize it. And if you want to normalize my pizza, you just say my pizza is equal to my pizza. Now that it is, color channels are always the same. It's between 0 and 255, so we just divide everything by 255. And now we go and run my pizza and see if it's normalized. No, something's wrong. TF image, decode image. Did I do this wrong? Is it decode image or decode images? I called it my pizza. It's an unsupported object type. Did I upload that properly? Oh, no, I need to read the file in. That's what the difference is here. So I'm just going to copy this. This is the same stuff. So I'm going to copy this, and then I'm going to go to correct that error is, I'm going to go my pizza is equal to, and tf.io.read file, and throw that in there, and get rid of the extra quotes that are inside of here. Those. Now it should work, right? Yeah. And everything's normalized. So it's a 256 image by 256, and 3 is represented with the RGB channels, and all of the data has been normalized, okay? So that's the process of taking an unknown image and basically putting it into a format so you'll be able to analyze it and test your model on it. Okay, so now what we want to do is go and make a prediction on whether this is pizza or this is a hot dog. So we just go predict like that. And what it's going to do is it's going to tell us how likely the image belongs to a class inside of our model. So you go TF, I have to change the dimensions on this. And how you do that is expand dimensions. And I will go my pizza. And axes is equal to 0. And it's my pizza underscore. There we are. And, okay, for a minute. All right, and what is our prediction? So this is going to be, how close are we here? All right, 95%. So that's about as good as you want. And let's go, I've jumped ahead of myself here. Let's go and come down here. Let's just keep writing code. I'm just ignoring all the other stuff that's here. Remember we had our class names. Whoops. Class names. Okay, hot dog and pizza. At this point, I think everybody at the very least knows that we are analyzing pizza and hot dogs. Okay, so let's come in and grab in and put another code block down inside of here. And predicted class. And now we're going to see if the prediction is whether it's pizza or it is a hot dog. So let's just round this. It's going to be 0 is hot dog and 1 is going to be pizza, because that's the order I have them in here. So prediction like that. And this is class names is what I called that. So let's throw class names inside of there. And predicted. So now we get to see if our model will work with something, and you can see yes. So it looked at a completely unrelated image it's never seen before, and it said this is pizza. All right. Let's go and get rid of whatever. To finish this off, okay, so that's ridiculous. We just we taught our computer to be able to tell the difference between hot dogs and pizza. I can't think of anything much better than that. Oh, somebody was telling me an error that how to correct an error. I should always look down there. Okay, so how do we save this model? We went through all this work to create this model that is highly accurate in predicting whether something is a pizza or if it's a hot dog. How do we save it? Well, we just go model 5 and save, and then we give it a name. So let's just call this binary CNN model 5. There it is, and it saved it. And whoops, did it? Yeah, it wrote it. And if you want to test or if you want to reload your model after you've created it, you just go saved model is equal to tf and caras dot models and load model, and you're going to just type in exactly whatever you named it before, and it's going to load it by name. So let's just go in here and grab this and paste that inside of there. And now what we can do is go saved model 5 dot evaluate and validation data and norm. And let's see how accurate it is. If it loaded my model, it did. And the accuracy for it is 82%. All right, there you go. Taught you a lot of stuff in this video. Hopefully somebody out there enjoyed it. Thank you, Vapula87. I'm glad you enjoyed the stream. I'm going to try to teach transfer learning along with a whole bunch of other things. Next Wednesday, noon Eastern Standard Time. You can go on my Discord or something if you want to make sure. Let's see. I can post a link to my Discord in the description for this video, because that's where I always post everything. But I also, probably the Discord's the best place. I don't know. I'll just post a link to my Discord in this video. And also all this code that will be heavily commented is going to be uploaded to GitHub. Everything is 100% free. I don't sell anything. And there you are. I just want to say thank you so much for your, well, thank you, the Lyrium Trigger. I greatly appreciate you guys stopping by. It's way more fun to do these live streams than it is to do anything else. And I think, I'm hoping someday it catches on. Just want to say thank you. Yeah. All right, cool. And anybody else have any other questions? Zen Fortitude, thank you very much for subscribing. I greatly appreciate that. That's all right. Well, thank you for showing up at all. And the whole video is going to be on Twitch as well as on YouTube anyway, so you'll be able to, do whatever. For anybody that's interested in what's coming up, I'm going to do a lot more machine learning videos. And I'm probably going to do a video on my progress on learning guitar in 30 days. How's my chess journey going? It's going terrible. This past week and a half, I haven't really been able to study because I've just been so busy doing other things, and my chess rating fell off a cliff. I've just been playing terrible, so what can you do? If you want to ask me any other questions, feel free to ask them. Otherwise, I'm going to end the stream, and I'm probably going to go run and then get back to doing all of my other work. All right? Well, thank you to everybody that joined me. I really, really, really do appreciate it. And I'll do my best to make another live stream on machine learning next Wednesday at noon. And otherwise, I will catch everybody next time.